We are very happy to have Lorenz from IS, and he will tell us about the partition functions of the tensionless string. Please start.
Oh, thanks very much. Yeah, thanks. Thanks for the invitation and for letting me virtually be at the West Coast. All right. Yes, I will talk about the recent paper I wrote, which is about the ADS3 CFT correspondence, but it's a very special limit of that. So, and where the string becomes tensionless. So that's why I call it partition functions of the tensionless string. So the idea of this talk is to give a motivation why you should look at this particular limit and care about this tensionless limit of string theory. And we will look at this tensionless string on different ADS3 backgrounds. But they don't have to be globally ADS3, they can be only locally ADS3, like we do for 3D gravity. And these different backgrounds will be described by different worksheet theories. So I will quickly go through how that works in constructing these theories. And then I will show you one sort of computation that you can do, namely to compute the corresponding string partition function on one of these backgrounds. And I will pick the sort of simplest one, which is thermal ADS3. So the idea is to compute that string partition function. We can do it to one loop. And then from here, there are some interesting puzzles and physical lessons, I think, to be learned. Yeah, and after that, I will just make some comments on how the higher genus case, more complicated geometries should work. But here, I cannot really do any computation right now. And then I will end with some open questions. There are many, I think. OK. So let's start with the basic setup. So as we know, whenever we want to compute some gravity partition function in some semi-classical way, then this requires summing over all the geometries. So and geometries means continuous parameters, but also topology. So we might also need to sum over different topologies. So in the context of ADS-CFT, we can make this a bit more precise. So in particular, if we want to compute some boundary partition function, then in order to reproduce it, we need to sum over all the possible bulk geometries that have that given boundary as a geometry. So by the way, one thing, since we are only 20 participants, I think we can do it kind of informally. And if you guys have questions, you should interrupt me at any point. All right. So for instance, one example where this was made very precise recently is JT gravity. So there we have a 2D bulk theory and a 1D boundary theory. So we can compute, for instance, the circle partition function in the boundary. And if we want to compute this gravitationally, then we should sum over all the possible bulk geometries. So the simplest one would be just a disk, where you just fill in the circle. But then there is a bunch of higher genus corrections. So you can put like these handles to the disk. And you need to sum all of those. And then there are even some non-perturbative completions you have to worry about. But but you have to sum all of those to reproduce the boundary circle partition function. So in general, a question you might have, or that is people have, of course, is over what kind of bulk geometry should we sum? So should we sum over any bulk geometry that comes to our mind? Are defects, singularities allowed, and so on? So especially in 2D, perhaps the situation is still kind of clear. So you have to sum over, there's just this genus expansion, but if you go higher in dimension, there's a whole zoo of manifolds you could potentially sum over. So you might worry, what should you sum over? And the situation becomes even more interesting if you consider the case of a disconnected boundary. So for instance, again, for JT gravity, you could compute holographically the partition function on a disconnected product of two circles. And again, you fill in the circle in all kinds of ways that come to your mind. So for instance, you can have two disks that just fill in the two circles, but you also could have the cylinder topology that connects the two circles. If you compute this in a boundary, so if there's an ADS-CFT pair, I guess you have heard the story, then in the boundary, the partition function on the disconnected sum of two circles is just the product of the partition functions. And in the bulk, basically the existence of this wormhole topology spoils this factorization. So this guy is a product of two partition functions. This is also a product of two partition functions, but this one leads to non-product. And the way out of this problem is that the dual CFT is not really one CFT, but it's an ensemble average of several theories. So if you do this ensemble average, then basically this guy also in the boundary is no longer a product of two partition functions. And also, so here I also want to ask, how is the factorization restored when there's only conjecture to be single boundary theory? So when we have ADS 5 times S5, then we know that there's only superior Mills as boundary. So we cannot play this game in ensemble averaging over superior Mills. So there has to be some different mechanism that that ensures the factorization, some magical cancellation of all these non-factorized terms or something of the sort. Okay, so basically these are the two questions I want to address. And I want to do it in not by doing ADS 5 times S5, because that's way too hard, but I want to use a different ADS CFT dual pair where there's only single boundary. So contrary to the case of JT gravity, I want to have an ADS CFT pair where we have only single boundary, and usually these pairs come from string theory. So, and the concrete one I want to use is the one where on the boundary you put the symmetric product orbifold. So that's a 2D CFT, and the target, so that target space of that CFT is n copies of the 4 torus, and then you mod out, you take the orbifold by the symmetric group that permutes these tori. So that was conjectured to be dual to the string background ADS 3 times S3 times T4, already in the first paper by Madasena. And there's the problem in this duality is that on both sides you have a very large moduli space or conformal manifold. So here, of course, you can change the shape of the torus, but there are also other moduli in the problem. And also the string background ADS3, S3, T4 has some large number of moduli. And for a long time, it was not known what is the precise moduli on the bulk side that correspond to the symmetric product on the boundary. And that was recently clarified. So the conjecture is now that the symmetric product orbifold is exactly dual without any same conformal manifold or deformation of, but it's exactly dual to string theory on ADS3, S3, T4 with pure NS background, and it has exactly 1 unit of NS flux. Okay, and so I want to use this duality to answer these questions or ask these questions because both sides of this duality are sort of simple. So the boundary is a 2D CFT that's an orbifold of a free theory. So you can compute essentially everything you want to compute in this CFT. And similarly, the bulk side is relatively easy because it's a pure NS background flux. If you have pure NS background, then you can give a worldsheet CFT description of this string background. So at least within perturbative string theory, you can compute also on this side. So you can ask these questions. Okay, so that's kind of nice because that's one correspondence where you can compute many things, contrary to say ADS 5 times S5. But there's a price to pay. The price is that the string theory is perhaps a bit removed from our everyday intuition. So in particular, it's tensionless. And so in one sense, it's tensionless is that you put exactly 1 unit of background flux. So usually you're used to thinking about supergravity where you have some large number of background flux, and then you put some strings on top of this. If you have some large flux, then in particular the geometry is big. So the string length is very small to ADS radius. That's the usual regime we're thinking about. And in this case, where you have this 1 unit of flux, the size of ADS is of the same order of magnitude as the size of the string. Or in other words, the tension of the string is very small. So that means that the string is somehow super big, and so most of the strings will somehow wind around ADS in some way because they're very extended. They're not point-like. Okay, this background is also tensionless in a more precise sense than just these pictures, namely in the sense that there are many space-time higher spin fields and massless higher spin fields. So usually if we're in flat space, then the string spectrum has like the graviton and the B field and so on. These are the massless fields, but we don't have any field of spin bigger than 2 that is massless. So all of these are massive. And if we take down the string tension, of course, they become lighter, these massive fields. But in the flat space, you can never make them strictly massless. So in ADS, you can do this because you have some additional length scale. So you have the size of ADS and the size of the string. You can make the string length very big compared to ADS. And then these fields become exactly massless. So you have a whole tower now of massless higher spin fields. Yeah, so in that sense, it's really tensionless. Okay, so yeah, what we want to do now is to consider the string on different background geometries and try to answer these questions. And there's immediately one conceptual problem you run into, namely the concept of geometry becomes somewhat murky in this regime. So it's not clear how you would define it. So what I mean by geometry always is a fixed worldsheet theory. So this is something that is still well defined. If you have some target space geometry that is big, then it corresponds to some worldsheet theory. But even if you have some very low number of fluxes, you can always talk about the worldsheet theory. So what I want to do is to describe the worldsheet theory of these different sort of locally ADS3 backgrounds, and then perhaps sum over them to get some boundary partition function. Okay. And so to have a consistent string background, we need these backgrounds to be at least locally ADS3. So I want them to be locally ADS3 times H3 times T4, but perhaps not globally. And to simplify further, also I want to talk just about the Euclidean case. So instead of Lorentzian ADS3, I will take Euclidean ADS3, which is the same thing as hyperbolic space. So actually, I will talk about this. So now what I simply want to do is to take quotients of these spaces, because if the only way to have a locally ADS3 times S3 times T4 or H3 times S3 times T4 is if that thing is a quotient of H3 itself. So that's exactly the same thing we would do in 3D gravity, for instance. So the backgrounds I want to consider are like supersymmetric analogs, because the whole thing is supersymmetric, of hyperbolic manifolds, and all the hyperbolic manifolds you can write as H3 mod G, where G is some discrete subgroup of the isometry group of this H3, which is PSL2C. Okay, and basically you can engineer a whole range of interesting geometries just by taking quotients. And again, so the guiding question in this exploration is, what bulk geometries do we need in order to reproduce the boundary partition function that lives now on the boundary of this quotient space? So this quotient space might be thermal ADS3, for instance. That's the example we will look at. The boundaries are 2 torus. And so we might try to compute the boundary torus partition function by summing over several of these quotients. Okay, so that's the basic setup. Is it clear what I'm trying to do? All right. Good. So then let's give a quick review of how these locally ADS3 or Euclidean ADS3 backgrounds work. So this is basically copied from the paper by Malone and Witten, where they explain it very nicely. So the main backgrounds I want to look at are ones that have a single torus boundary, because that's just for computational simplicity. If there's higher genus boundary or something, it becomes very complicated. Okay, and so there we know some familiar ones are like thermal ADS3, the BTZ black hole, and so on. In all these cases, the group, so yeah, let's start with thermal ADS3. Then the group by which I want to mod out is just the integers. And it's generated by a single diagonal matrix. So it's an infinite cyclic group. And this diagonal matrix you can take to be this e to the pi it. And you can also arrange t to be in the upper half plane. And then t will be interpreted as the modular parameter of the boundary. So the boundary will be a torus and has a modular parameter, and this t will be the modular parameter. Okay, I'm reserving tau for later, so that's why it's t. Yeah, and this group, you can see that it gives a torus because it acts on the boundary coordinate by Mobius transformations, but it's diagonal, so Mobius transformations is just a scaling, like that. And the scaling, you can just bring, so if you have any x by that group action, you can bring it into a fundamental domain. And in this case, the fundamental domain is the annulus. So you can bring it always in this annulus, and now the group action identifies the inner circle of the annulus and the outer circle of the annulus, and that's why you get the torus. Okay, so let's draw a picture of that thing. So the red annulus is the boundary annulus that we just talked about, the boundary fundamental domain. And the group action I drew with these blue arrows here, they identify the inner and the outer circle of the annulus, and you see the boundaries indeed the torus. And now what happens in the bulk? So bulk goes in this direction. This is the Poincare coordinate z. Is that this annulus will basically be extended to like two hemispheres. So the inner circle becomes this hemisphere and the outer circle becomes the big hemisphere. Again, the inner hemisphere and the outer hemisphere are identified by the group action. So you can take this to be the bulk fundamental domain if you want. And if you think a bit about this, so the boundary was a torus, and now we fill that torus in with this bulk, and the whole geometry just becomes a solid torus. Okay, and so that's the geometry. But if we want to interpret it physically, we have to make, I have to tell you what is time, because that's a Euclidean geometry, so I can choose what is my time direction. And the physical interpretation of this geometry is actually different depending on which time arrow you choose. So for instance, you could choose this time arrow, this time arrow for time. So that's like what we do in radial quantization. And then you see that time runs around along this arrow that is indicated here. And so this arrow is non-contractible. So it's one of the cycles of the torus. And if you slide it into the bulk, it still becomes a non-contractible cycle. So it's the cycle that runs from the inner hemisphere to the outer hemisphere, and then it's identified again with the inner one. But contrary is the situation where you take the time cycle and the boundary to run around the circle. So that's the second option here. If you do that, then you see that the cycle runs around it, and you can just slide it in the bulk and contract it here in the middle. So in one case, the time arrow is non-contractible, and here is contractible in the bulk. So that's why they are physically different. And this guy is the usual thermal ADS3 geometry, where you can also think about it as some cylinder, and you identify the ends of the cylinder, and now you get the Euclidean time that runs in the cylinder. And for the BTZ black hole, on the other hand, the time cycle is contractible. Okay. Yeah, and in general, you could also even take your time cycle to be any linear combination of those, and you get this famous SL2Z family of Euclidean black holes, where you basically, you take like any combination of the A and B cycle of your torus to be your time cycle. So yeah, and just a quick reminder, we're talking actually about some supersymmetric analog. So what we will actually talk about is not some subgroup of PSL2C, but about some supergroup, which is this PSU1,1/2. But you don't have to worry too much about this. So this is basically this PSU1,1/2 has this bosonic subgroup, this SL2C, times an SU2, and this SU2 acts on the 3-sphere that is also in the geometry. And you can still write the orbifold or the quotient group that we're talking about is still the integers, and it's generally generated now by a diagonal matrix in this supergroup. And you, in particular, on the ADS3 part, it acts exactly the same. And on the S3 part, there's this additional matrix. And yeah, now this Z that appears, you can interpret as the chemical potential for this SU2. Okay. So I hope that was not too crazy, this reminder. And another interesting geometry that I want to mention is conical defects. So because the conical defect geometry has a singularity, and so we can use it to probe our questions about what should we do with singular geometries? Should we sum over them or not? So in 3D gravity, there's actually an interesting discussion about this right now. And yeah, so that's why I discuss it. And you can, again, if the deficit angle takes some specific form of the form 2 pi times 1 minus an integer to the minus 1, then you can again write this as a quotient of global ADS3. And in this case, the orbifold group, the quotient group, takes the same form. So this factor is the same one as before. It's just that you need to rescale t by this m in order to keep its interpretation as modular parameter. And now you add a second generator that rotates the whole picture. So the picture is the same as before, except that you have this additional generator that rotates the whole geometry. And I plotted it for m equal to 5. So now the new fundamental domain is just this green slice of your annulus. And you see if you do this additional rotation, then there's a fixed point in the bulk or fixed line in the bulk. And that's why your conical defect sits. So the boundary is still a torus, but now the bulk has this conical defect on this line. Okay, and so in particular, it's a singular geometry. Okay, there is one more torus boundary geometry, but I will not mention it. And so just a very quick nod towards the multiple boundary case. If you have multiple boundaries, then the boundaries necessarily have genus at least 2. So you cannot have multiple genus 1 boundaries. That's a bit of a problem because if you want to probe this disconnected boundary case, you have to necessarily go to genus 2. So that's why it's a lot harder to say something about this question than about the first question, which was which boundaries you have to, which geometries you have to sum over to get the boundary torus partition function set. But yeah, you can still get, for instance, 2 genus 2 surfaces as boundaries by taking the quotient by what's known as a Fuchsian group. The Fuchsian group is just a subgroup of PSL2R, a discrete subgroup. And if you take it to be of PSL2R, the subgroup, then it fixes the real line in the boundary. So again, it acts by Mobius transformations. So the real line is fixed. And that leads to the fact that you have like 2 copies of the same geometry. One is in the upper half plane and one is in the lower half plane of the boundary. So, and you get basically a wormhole that connects these 2 Riemann surfaces. And yeah, so, and in particular, these 2 boundary surfaces have the same moduli. If you want them to have different moduli, there is a different generalization to this quasi-Fuchsian group. But I don't want to get into it. I will just for so you understand that it's much more complicated, and so we will mostly focusing on this partition function story. Okay, any questions on this? All right. Good. So now we want to construct the corresponding worksheet theories. And that's actually quite simple because we saw that all these backgrounds by construction essentially are orbifold backgrounds. So whenever you have now a target space that is an orbifold, then the worksheet theory that describes that target space should just be the orbifold of the worksheet theory that describes the original target space, which was global ADS3. So the message is, if you know global ADS3 worksheet theory, then you just take the orbifold by the corresponding subgroup of PSL2C. Okay, and so then you just have to construct a worksheet theory for ADS3, S3, T4, or for one unit of an S and S flux. And yeah, unfortunately, it's not really so nice to do it within the standard string theory formalism, which is the RNS formalism, perhaps. But you can do it in a different formalism. So there's some problem that if you go to one unit of an S and S flux, then some unitarity breaks down in the worksheet, and it's a bit, yeah, convoluted story, but you can cure it by going to this other formalism, which is called the hybrid formalism. Basically, in the hybrid formalism, what you do, you don't make space worksheet supersymmetry manifest, but you make spacetime supersymmetry manifest. Roughly, you can think of this hybrid formalism as being some pure spinor formalism in 6 dimensions. So it's just pure spin on ADS3 S3, but still RNS on the T4, essentially. But the point of the story is that you describe your ADS3 S3 T4 by some super WZW model, which is again based on that supergroup that we encountered already before, which is PSU 1,1/2. And the level of that supergroup coincides exactly with the amount of an S and S flux. So in our case, we will take the level to be 1. And then there's, again, this T4 is basically described in the RNS formalism. So it's just 4 free bosons, 4 free fermions. And then there's a bunch of ghosts that impose some BRST constraints, like we have also in the RNS formalism. They're different ghosts, but still it's just BRST. So yeah, the message is that these T4 times ghosts is kind of easy to deal with for the purpose of partition functions, and the magic happens in this PSU 1,1/2 level 1 WZW model. And rather, I'm calling this PSU 1,1/2 because I don't have a better name. That's actually the Lorentzian, would be the Lorentzian geometry. I actually need the Euclidean rotation of this. So you could call it perhaps Euclidean PSU 1,1/2, but I think there's no name that anyone gave to this sort of geometry. Okay. Good. So yeah, essentially all we need to know is what, if we know the partition function of this PSU 1,1/2 level 1, then we know what we need to do. We just need to take the orbifold by the corresponding subgroup of this essay of this PSU 1,1/2 and just use CFT2 techniques to compute the orbifold partition function. And that will give us the string partition function as well if we impose all the physical state conditions that come from the BRST cohomology here. Okay, so that's the plan. Good. So let's do it for thermal ADS3, so you will see how it works. So here, of course, it's particularly simple. You take the orbifold by the integers, and so that's exactly this orbifold group we saw above. It's generated by the single diagonal matrix inside PSU 1,1/2. And given this, now you can now compute the Worksheet torus partition function. I should say that the PSU 1,1/2 level 1 WZW partition function is known, so you can use it to compute this Worksheet partition function. And it's kind of a not too complicated computation, but I just want to show you the result. It turns out that the result is most nicely written as a sum over 4 integers. So the appearance of 2 integers you can easily understand because we're taking an orbifold by integers. So twisted sectors of this orbifold will be described by 2 integers. But there's 2 more integers, and basically these arise because strings can wind around ADS3. Maybe let me make a picture. So if I draw ADS3, so this is like a time slice of ADS3. If you take, let's start perhaps with global ADS3. So global ADS3 is a long cylinder. We make a time slice and we just get a disk. So that's the disk at some fixed time. And now we can have some strings in that background. And as I said, most strings will be winding. So most strings will look something like this. They will be very large and close to the boundary. And you see that now you could also have a string that goes like this. So there's a winding number that this string can have. It doesn't look like a winding number because topologically you think you can just contract that string. But actually it turns out that there is this is a well-defined winding number. And you can, yeah, it corresponds to some number in the quantum theory that is associated to the corresponding representation of the symmetry algebra. Yeah, the precise definition doesn't matter, but there's this winding number. And basically because of this winding number, there are additional integers that can occur here. So in total, it turns out that for a torus, so the worksheet is now a torus, and the boundary will be also a torus. And all these integers basically tell you about different windings of one torus inside the other torus. So this will come back later. Okay, so and in one of these, so you can think of these as being Worksheetian centon sectors. And so one of these sectors takes some kind of interesting form, so I also want to show it. So, okay, there's first is this imaginary part of T. This comes because if you compute some orbifold partition function, you need to include like 1 over G of the orbifold group. But in this case, these are the integers. So you need to regularize this. And this thing is just, you can also see as the volume. So at least it's proportional to the volume of the resulting orbifold space, right? So it's you can see that this guy should be proportional to the volume of thermal ADS3. And indeed, the volume of thermal ADS3 is imaginary part of T up to some pi squared or something. So this is how this factor comes about. And then you get some kind of very interesting factor that is a delta function. So it turns out that this partition function is generically just 0. And except if this t, which was the boundary modular parameter, and the tau, which is the worldsheet modular parameter, have some very specific relation. Namely that, I wrote it here again, the t is related to tau in this way. And yeah, I will have to say much more to say about this, I guess, later. But so yeah, we refer to this that the partition functions, and in fact, it seems like any quantity in the string theory localizes in the moduli space of Riemann surfaces. So in this case, the moduli space of Riemann surfaces is parameterized by tau. So it's a 0-point function in the torus. And this guy localizes completely in this tau space. And this property seems to be true even of correlation functions and so on. So it seems to be like some generic property. But to be honest, I don't have any, like, I cannot prove it to you in generality or something. I just observe it in different contexts, like correlation functions, partition functions, and so that it happens. Right, yeah, more on that later. Then we have some phase factors. These are not too important. But what I then want to, you to pay attention is this T4 partition function here. So this is just a partition function of the T4 sigma model. So that's a good sign, certainly, that it appears, because we want to make contact to the boundary theory, which was the symmetric product orbifold of T4. So we better need that to be there. However, it's a bit strange that there's just a T4 partition function. So by the way, this Z, again, was the chemical potential for the SU2. You can put that to 0. It doesn't change a lot. And this A half, B half are just some spin structures on the T4. So it's also not too important. But what's strange about this is that there's just a T4 partition function. So T4 has just 4 oscillators, 4 fermions, 4 bosons. Whereas if you're computing something in string theory, you would think that there are 8 transverse bosons and 8 transverse fermions, right? So here somehow half of them are magically gone. And so how does it happen? So the kind of rough intuition is that when you make your ADS smaller, so remember it was of unit of string length, so ADS is super small and S3 is super small. And then the intuition is that somehow the string doesn't have enough space to oscillate in these directions. So all the transverse oscillations happen only in the T4 part, but in the ADS 3 times S3, because it's so small and cramped, somehow the string doesn't have space. So that's with a very rough intuition. The bit more precise intuition is that if you that this is actually something you kind of know, because if you look at, say, the SU2 WZW model, then you probably know that if you take K very large, the level, then this will be like a 3-sphere with very large radius. Then this looks approximately like 3 bosons because it's almost flat, like very roughly. But in any case, there are 3 oscillators worth of degrees of freedom, or in other words, the central charge is 3. So it looks like 3 bosons. On the other hand, if you put this level to be very small, and in the extreme case, you put it to be 1, then this guy is just 1 free boson. It's a free boson at the self-do radius. So also in this case, if you go from large level to small level, you lose 2 bosons. The degrees of freedom go. And in this case, this is sort of a more extreme incarnation of this phenomenon, that when you go to very small flux, then you lose more and more already at, like, say, flux 3, 2, you lose more and more degrees of freedom, and then suddenly at flux 1, you only have a single T4 left. Okay, so these are the sort of 2 magic properties, the delta function and the fact that you have only 4 oscillators instead of 8. Okay. Good, so then let's come back to this delta function. So we see that the partition function localizes on these configurations. So what do these configurations mean? The special meaning of this is that if there is this relation between the worldsheet modular parameter and the boundary modular parameter, then there exists a holomorphic map that maps you from the worldsheet torus to the boundary torus. So in other words, and this one is a covering map. So there's the worldsheet torus covers the boundary torus, and that's sort of consistent with the picture we had above. That yeah, let me try to draw it again. So this was again just a time slice because I'm just not able to draw the whole torus, but you should think that the torus extends in the 3rd direction. And then you have like strings that wind in some way like this. And now you should think that these strings cover the boundary. So you could map the string to the corresponding point of the boundary. That would give you this holomorphic map. So the worldsheet torus is supposed to cover the boundary torus by some holomorphic map. The fact that it's holomorphic is not so clear from this picture. Yeah, and this imposes, the existence of this covering imposes a restriction on the moduli, which is exactly this. And for this relation, this covering has a certain degree. So this degree is just how many pre-images some point has. So in this case, the degree would be 2 because 2 points are mapped to 1. And the degree turns out to be this determinant, which also appeared in the partition function. So this determinant is what generalizes to the torus case, this winding number that we saw. So in general, this worldsheet wraps the determinant of ABCD number of times around the boundary. Okay. Good. Is this clear? Are there questions on this? Yeah, again, please feel free to interrupt me at any point. Okay. Good. If it's clear, then let's try to go on and compute the string partition function. However, there will be a kind of immediate problem that rises because it turns out that you're computing in different ensembles in the boundary in the debug. That's kind of an interesting puzzle. So if you write down the symmetric orbifold, then you have this n number of copies of T4. And I actually haven't told you what n is in the beginning, so you should have me bug me about this. But n corresponds to the number of fundamental strings in the background. So I told you that there is 1 unit of NS background flux. So that, in other words, you can think of as the geometry as being constructed from 1 NS5 brane, and then you put some number of fundamental strings. So this is the S-dual picture of what you usually have if you have the D1, D5 system. So that's the usual way of constructing these backgrounds. You do an S-duality, then you get like a fundamental string and NS5 branes. And the fact that you have 1 unit of NS flux means you have 1 unit, you have exactly 1 of these guys. But you can still have any number of fundamental strings, and this number is n. Okay. And n, if you solve the supergravity equation of motions, n sets also the string coupling. So n goes like 1 over g string squared. So, but I should mention that this is some relation in supergravity. So it's not super clear to me whether it should hold in this limit or not. Fortunately, I will get around this issue mostly because I'm just talking about tori, and the torus partition function is actually independent of this G string. So, but that's something that puzzles me a bit. Okay, yeah. So in this, we saw that in symmetric orbifold, n corresponds to the number of fundamental strings. And now if you do string perturbation theory, then you wouldn't fix this number of n. So you can have any string perturbation theory, you can have any process, and like in this process, in the meantime, n can get larger and smaller because you can create strings and so on. So it seems that in string perturbation theory, it's very hard or impossible to reproduce partition function of the symmetric orbifold actually, because n is not fixed. However, you can compute something related, which is like so basically this you can think of as being a canonical ensemble because number of strings is fixed. But it's convenient now to go to some grand canonical ensemble, where instead of fixing n, you fix some associated chemical potential, which I call sigma. So you compute some grand canonical partition function. So from a boundary point of view, this guy depends on the boundary modular parameter, this chemical potential, as well as on the SU2 chemical potential. And you can think of it as just being the sum over all the symmetric orbifolds. So it's like the generating function, these partition functions. And this P is e to the 2 pi sigma. So this is what I claim, and actually what Kim and Parati claimed, that the string perturbation theory should compute. Okay, so now we just need some way of introducing sigma on the worksheet. And that is also explained in this Kim and Parati paper. And all you need to do is you need to add a marginal operator in the worksheet. And that marginal operator is simply the vertex operator that corresponds in space-time to the identity. So in particular, since there is supposed to be a correspondence, every operator in spacetime should have some analog on the worksheet, and in particular, spacetime identity operator. And this guy just counts essentially the number of strings. And and on the worksheet is some marginal operator that you can add. And if you add it to your theory, then this is basically building in some counting thing that just counts number of strings. So the OPEs of this guy with everyone is sort of trivial because it's the identity operator. The only thing that is non-trivial is the eigenvalue. So it acts diagonally always, but it has different eigenvalues, and the eigenvalue is exactly this number of strings. And if you do that, what you get is that the worksheet torus partition function, if you now add this operator to it, we saw what it is above, but now it gets slightly modified because of that. And you get this additional factor, which is p to this determinant, where p again was this e to the 2 pi sigma. So that makes kind of sense because the determinant was the degree of the covering map. So how many times the worksheet wrapped the boundary. And in particular, a single string, you see that a single string can contribute to not only one n in the boundary, but to several n by winding several times around it. So if for a third time I draw my picture, and this string winds twice again, then this string would contribute 2 to the boundary charge of n because it winds twice around the boundary. Okay, good. So that was one issue with computing the partition function. There is another a bit subtle issue, which is the sphere partition function, which I didn't talk about so far. So we wanted to compute the string, say, one loop partition function, but I didn't even talk about the tree level. So I should have started with the tree level. And of course, there's a sphere diagram, but it's a bit subtle because the sphere diagram can be changed by the boundary conformal anomaly. So it's not universal. And so I basically, and also it's hard to compute on the worksheet because there's an infinite Mobius symmetry remaining on the worksheet. And so naively you divide infinity by infinity. So I'm not aware of anyone making this very precise, how you can compute this actually from a worksheet. And however, if you just assume the boundary to be a flat torus, then it's just fixed by boundary conformal symmetry. So that's what I will do. So let's just assume the boundary has conformal symmetry and we are on the flat torus. Then it's just what it does is just to insert this, you know, if you compute some partition function in 2D CFT, you just put this factor in there. And that's what the sphere partition function should account for because that comes from the conformal anomaly. So I just put this factor by half. So if I'm not taking the sphere into account, I would basically lose this factor, which is also not too bad. But yeah, so if you do that, then all you need to do is to account for it because this, I mean, it's correctly accounted if you shift the chemical potential that we just saw by some multiple of imaginary part of the boundary modular parameter. So yeah. Okay, so this is another subtlety you have to take into account. But with these things, you can now write down what is the string one loop partition function. And after that, we can finally talk about interesting physics. So, okay, thermal ADS3 partition function, you need to take some exponential because you need to account also for disconnected worksheets. Until now, we just talked about single torus. And then basically you write down what I copied down what we had above. So you sum over these 4 integers, you have the delta function, you have this p that measures the number of strings, you have some uninteresting phase, and you have the T4 partition function. And now it's contrary to usual string theory, it's super easy to do this integral of a fundamental domain because you have a delta function. So it's just combinatorics, or yeah, it's just like keeping track which integers contribute, which don't contribute. So if you do it, you get just an exponential of basically the torus partition function evaluated at different modular parameters. So you sum now of 4 integers, you have like 2.5 remaining roughly. So there are 2 integers as well as a cyclic integer. There's this p, and you evaluate the torus partition function at different modular parameters. And you can think of this expression, it's some useful way of thinking about this, is that this corresponds to all the coverings of your boundary torus, holomorphic coverings, I mean, and then you take p to the degree of this covering, and you evaluate the T4 partition function on the cover, neglecting issues like spin structure and so on.
A question.
Yeah.
Sorry, is it okay if I ask a question? Can this be written as a HEP-QIS operator acting
Yeah.
on?
Yeah, that's exactly a HEP-QIS operator. Yeah.
Okay, great.
Yeah,
Thank
you can write it like this. I guess something like this. P to the L over L. Oh.
All right, I think your screen disappeared actually.
Yeah, sorry. I guess it should come again now. All right, yeah. Sorry about that. I don't know what happened. Okay, yeah, so it's this expression.
So this is also just the DMVV, oh, I see. This is the DMVV formula.
Yeah, exactly. So that's actually my point, that this is exactly the same as the symmetric orbifold partition function. Yeah.
Okay, thank you.
We'll get to this in a second. Yeah, thanks for the question. Yeah, in general, a useful way of thinking about this is that you just sum over all the covers of the torus. You put P to the degree of that cover, and you evaluate the T4 partition function on that cover. And here I don't need the cover necessarily to be connected. It could be disconnected. And the idea would be essentially that what we saw from the computations, that this covering corresponds exactly to the different worksheets that you have, different configurations of worksheets. Okay, yeah, but as Alex was saying, the very interesting thing is that this is exactly equal to the symmetric orbifold partition function. So we started out in computing one loop of thermal radius 3, and we found already the full answer for the boundary theory. There's nothing missing. The only critique you could have is that you have a fixed boundary spin structure. So there's only one spin structure of boundary appearing. And that's sort of built into the computation. But apart from spin structure, we found the whole answer, not just some part.
Right, can I ask, so why does this work?
Why does it work? Yeah, I guess that will be my main question later. Why does it work? Do you mean technically or physically or?
Physically, like why? I mean, because you only did one loop strings in the bulk.
Yeah, right? Okay, yeah, I guess if you could wait 10 minutes, I think I will probably answer your question. If not, then please bug me again.
Okay, thank you.
Thanks. All right. Yeah, and we can actually do the same thing on all the other backgrounds that I mentioned. So for instance, on the other SL2Z black holes or on the conical defect. And what one finds for a fixed boundary spin structure is that the grand canonical partition function is actually always the same. So it doesn't matter on what background you compute it, but you always get the same result. So if you do it in thermal radius 3 or conical defect and on any of these black holes, you get always the same. The only caveat is that you need to always have the same boundary spin structure. All right, so that's the kind of observation. Let's get now straight to the puzzles. Why does it work? So there are different levels of answer to this. Let's start with the technical answer, I guess, or technical worries that you could have. So we computed one loop string partition function. So the first immediate question you probably have is, okay, if you compute higher loops, then this should like do something and maybe destroy the answer. So I don't know how to compute higher loops explicitly on the worksheet. I'm actually working on it, but yeah, I don't know how to do it yet. But if you assume that this localization thing works, that seems to work in different circumstances. So the localization kind of conjecture that exists is always that whenever you compute anything in the string theory, the partition function or correlation function always localizes to holomorphic coverings of the boundary by the worksheet. So in particular, if you're computing now a partition function on a higher genus worldsheet, but the boundary is still a torus, then this would tell you that this has to vanish. The reason is just that the torus, the only holomorphic coverings of a torus are again tori. That just follows from the Euler characteristic of being 0, and so of any cover, if you compute the Euler character, is the degree of the cover times the original T2, so it's still 0. Okay, so that argument, if you believe that, again, there's no proof of this, then this will tell you that there's no higher genus worldsheet corrections to this result. So in particular, no perturbative corrections. Okay, so that's something I think in the future can be proved. what's much more murky is non-perturbative corrections to this. So you can ask, are there non-perturbative corrections that spoil this result? So there are essentially two kinds of corrections I'm thinking about. One would be some sort of de-instanton corrections. For that, you would need to first classify all the boundary, the possible boundary states, and see whether they can appear in some computation like this. So this is something that has not been done, but that's also potentially be doable. And perhaps you would see that they cancel, or they don't appear, or they don't exist. I don't know exactly what is the answer. So that's another type of correction. And maybe the worst of all is back reaction. So we're talking about some strings here that that can be super long. So these are strings that can wind, like basically. So in the symmetric obifold of T4, we have in particular strings states that that corresponds to strings that wind that wind n times around the boundary, but they are only one string. So in other words, you have one string that winds 1/g string squared many times around the boundary, roughly speaking. So that's a single string, but this and the string itself is light. But if you wind it that many times because of the tension, it becomes actually heavy, provided that this dictionary of n and g string holds. So you might be worried that this guy spoils your computation because you're perhaps not supposed to trust perturbative string theory in this regime. And in fact, we will see in a second that it does change the background geometry. And yeah, so you can be worried that this changes the spectrum, and I fully agree with you that this is a valid worry that you might have. So here, I guess that's at the heart why this works and why you can be worried about this. But I still want to go on and see, provided that this kind of picture still holds, if you add all the corrections, that you get still the what kind of physical lessons you can extract from it. Okay. So yeah, in particular, we saw that all the SL2Z black holes with the same boundary spin structure lead to the same string partition function. So that's very much in contrast to the classical Maloney-Witten computation or something like this in 3D gravity, where you would need to sum over all the bulk geometries and put the one loop correction. So here it seems you don't need to sum over bulk geometries. In fact, if you put all the bulk geometries, you would heavily overcount in the problem because you would add always the same term. So yeah, that's some revelation. And in particular, what this will mean is that you can, if this is true, you can reproduce any state in the boundary from the point of view of any bulk geometry. So you can start with thermal ADH3 and ask what is the BTZ black hole as a string state on thermal ADH3. So that's exactly what we will ask now. And another way to phrase this question is to ask, how is this consistent with the existence of the Hawking-Page transition? Usually we say in the boundary, we have the sphere partition function. And if you're computing the boundary torus partition function, say that at low temperatures, this guy is dominated by the thermal ADH3. And from the point of view of string theory, we would say the string partition function is always dominated by the sphere partition function that sort of sees the geometry. If you now raise the temperature in the boundary, then there's a phase transition from the thermal ADH3 to the black hole phase. But yeah, usually you have two different geometries that contribute differently. So how can it be that here you have only one geometry? The sort of answer is, again, that basically the torus can compete with the sphere. And it can compete because it includes strings that are so long and that are so heavy. And in terms of this partition function that we saw above, it's just the different terms in the sum over ABCD. These worldsheet instanton sectors can dominate. In particular, now, if you know which terms dominate, you can try to identify them with the classical geometries. So for instance, let's do it for the vacuum of thermal ADH3. That's a very simple state. So the vacuum of thermal ADH3 is mapped to the boundary vacuum as well. And now you just look, there's a gas of spherical strings because there's a non-vanishing sphere partition function. And then the state that is mapped to the boundary vacuum is the one that corresponds in the sum to A is D is 1 and B is equal to 0, C is equal to 0. So these are many toroidal strings. You need many disconnected worldsheets, but all of them map wind exactly once around the boundary. So in other words, this term corresponds to the term where the T and the tau are just identical. So the boundary torus and the boundary torus, the boundary and the worldsheet torus, they perfectly align. Okay, so that's the vacuum. Now, perhaps more interesting, what is the BTZ black hole? So again, one possibility of describing the BTZ black hole is in terms of geometry. You say it's the vacuum of the BTZ black hole. But another way is to describe it in terms of some excited string state on thermal 3, because thermal 3 captures the whole boundary partition function. So in this picture, it's a gas of spherical strings again. But now in this sum over ABCD, it's a different term. It's the one where AD is 0 and B is n and C is -1. So B is as large as possible. And this corresponds to only one single string. So you need only a single string, but that single string winds n times around the boundary. This is precisely the string I was talking about before. And remember again, n was super heavy. So it's many times winding. And this term says, I think that T is -1 over n tau or minus n over tau, something like this. Right. So that is what the BTZ black hole is from the point of view of thermal 3. And perhaps now it's not so crazy because that's something that was conjectured to happen a very long time ago, namely that there's a string black hole transition. That's the black hole. So if you make a black hole of size of the string length, then basically the system transitions into a perturbative string state. The perturbative string state is the one where you have a single long string that winds around the horizon. Here we're talking about Euclidean geometry, so there's no horizon, but still we see a long string that winds around the boundary of ADS2. Okay, so I think that's kind of a nice direct observation of this effect. Okay, we can also talk about the conical defects. And again, I need the deficit angle to be this, just in order to have some orbifold construction of that background. And if you track down what the state corresponds to the vacuum of the conical defect from the point of view of thermal ADS3, then it corresponds now to many toroidal strings that all wind m times around the boundary. So now this A is m, so that means that they wind n times around it. And so the basic message is, again, that sphere and torus can compete because the length of the string is super big. And so some things that you might naively think that are true are not really true. Okay, so that's all provided that you can trust this computation, at least qualitatively. And another way to say it is that any state you can see from any bulk background, but for instance, if you take the vacuum of one background, it's a highly excited state in another background. So I view it as some sort of kind of T-duality thing. So it's like some sort of string duality of the same boundary theory. Okay. Another question you might have is that how is that consistent with the existence of a hagedorn transition? Or not consistent perhaps, but so usually if we do string perturbation theory in some thermal background, then it does not make sense beyond a certain temperature, which is the hagedorn temperature. So there the free energy blows up a lot. Or also equivalently on the thermal cycle, you have a tachyon. So you might be worried that this happens here at some point, and so you should not be able to trust this computation if you raise the temperature beyond that temperature. But here this does not really happen because this hagedorn transition is a large n effect. And basically by introducing this chemical potential for n, we essentially cut off large n. And so there is indeed a hagedorn transition, but it depends on what this chemical potential is. So what you need in order for you not to have a thermal tachyon is this condition. So as long as you make your chemical potential large enough, it doesn't matter what your temperature is. So I think it's trustworthy, but if you cross that line, I'm not sure what is the physical interpretation. There's some phase transition happening there. All right, so these were the sort of puzzles and my answers to them. I hope that makes you sort of happy. maybe I have answered the question. I'm not sure. Okay. All right. So I guess I'm almost out of time. So if I can have like 5 to 10 more minutes, if that's fine. Yeah. Okay. Thanks. All right. So now I will just comment on how I would expect the higher genus case to generalize, and also the physically interesting case where you have a wormhole. But again, this is too complicated to compute for me at the moment, because you need to, first of all, look at higher genus boundaries, but you also need to look at higher genus worldsheets. So in particular, my argument that the higher genus worldsheet partition functions don't contribute was specific to the case where the boundary is a torus. So here, this will not be true. But you might try to extrapolate from the case we just discussed and use the physical lessons we learned to draw some qualitative conclusions. Right. So let's first go to a single, at least genus 2 boundary. And here, the bulk geometries are much more complicated than in the thermal ADS 3 case. So they can be handle bodies, or they can be also non-handle bodies. So handle bodies are just the sort of interiors of a Riemann surface as you would draw it on a piece of paper. But there you can also sort of add holes and like additional 3D handles in them, and you get these non-handle body geometries. So there's not the simple list like before of what the geometries are, but there's like a much bigger zoo. So it becomes more interesting whether all of these geometries could potentially be the same. So yeah, and the worldsheet partition functions would be non-zero now for different genera. So it's not that the genus cuts off at genus 1. Yeah, so that makes it much more complicated, obviously. But now you can hope or conjecture that the string partition function, if you compute it on any of these bulk geometries, but now you have to compute the full one, not just the one loop one, then you get the genus G symmetric orbifold partition function. All right, that's, I'm not, yeah, I hope this is true, but again, I'm not sure. Okay, and you can maybe even speculate even more that this is even true if you have disconnected boundaries. So if you have disconnected boundaries, then this would in particular imply that this grand canonical partition function on a connected background is just the same as on a disconnected background. And yeah, one thing I should perhaps mention, which I haven't underlined a lot, is that this equalities should not be super obvious. So it's basically, you can think of it as being a T-duality. It's not super obvious that these are equivalent. You have to do perhaps some Poisson reformation or some modular transformations. So for instance, to see that the BTZ black hole is the same as thermal ADS 3 is not super obvious. Also, the conical defect that is the same to thermal ADS 3, there's some reshuffling of the spectrum. That some states that were previously like usual winding strings are now twisted sectors of this orbifold and so on. Yeah, but so the idea would be that these things are the same, but it's sort of not obvious that they're the same. And in the connected background, this is the wormhole. The factorization would be not obvious, but it becomes obvious once you go to the disconnected background, because in the disconnected background, you manifestly write it as a product of two things. So that would be the idea how the factorization can be reinstated if you have a sort of wormhole. It's just that the connected is the same as the disconnected, but in the disconnected, for instance, the vacuum of the wormhole will correspond to some diagonal state in this partition function. Yeah, that's sort of the vision. All right. So with this, yeah, I have many open questions, as I'm sure you have, but let me add to these, which I think are the sort of most important questions and takeaways. So technically, the most important question is whether for me, is whether you can trust this computation. And if, why don't we have to take into account back reaction? And, or put differently, why are there no non-perturbative effects? In the symmetric orbifold, we can just observe that there are no non-perturbative effects, by the way. Because a non-perturbative effect, say if there is some d instanton, it will go like, in the air, will lead to a term like this. And this is like e to the minus square root of n. And there are no things in the symmetric orbifold that go like square root of n. So you so that's an argument why you shouldn't have any non-perturbative effects. Yeah, so you can also ask whether you should take into account non-saddle contributions. I've only talked about saddle geometries in the whole talk. So because we took some orbifolds of ADS3, But for instance, in JT gravity, all these geometries are actually not saddles, and they still give contributions. And similarly, in 3D gravity, there are also non-saddles that give contributions. For instance, there is a wormhole geometry that is T2 times an interval that doesn't carry a hyperbolic metric, so it's not a saddle. But still, you can compute what is the partition function in 3D gravity. So that's a computation that was done recently by Kotler and Jensen. So you might, first of all, worry that these will spoil the result because you should also somehow account for those. But in string theory, I don't know how to even set up the computation to account for those because I need some saddle background to expand around. And given that the other saddles were already included in the partition functions, you might also hope that the non-saddles are somehow included. But yeah, I don't know how to identify them somehow, as I knew how to identify the conical defect or the BTZ black hole. But that's something to keep in mind. Yeah, you might worry, or no, not worry. You might hope that there is actually some smart way to do it in the string partition function. And I think if there is, it could also teach us something about string perturbation theory. Because the point is that the answer is always sort of simple. So the answer that you expect, even for a high genus boundary, some wormhole and so on, is always that the same formula I wrote down before. So that the grand conical partition function is the sum over all the possible coverings. You put p to the degree, and you evaluate the T4 partition function on the cover. That thing is always true, even though the coverings might have higher genus and so on, and they're more complicated. But this is always true. So this tells you that it shouldn't be like impossible to do this computation because we know the answer, at least from. Okay, then physically you might be interested. So this is like a very far removed from anything you have seen. So you might worry what lessons carry over to larger flux or to other backgrounds. And for instance, there's also deformation of that point in the modular space, as I mentioned at the very beginning. And you might ask, if I turn on this deformation, does this story still hold, or how does it get destroyed? At some point, it for sure has to be destroyed because this black hole string transition is not supposed to hold for a very large flux. So at some point, black holes are certainly not the same thing as winding strings. Yeah, you might also ask, how does the Lorenz picture work? I have no idea. And finally, the kind of some speculation of mine is that we're essentially talking about some un-Higgs phase of string theory. So because there's all these higher spins fields in space-time. So this is like what Gross and Mende thought about the un-Higgs phase of string theory. There just should be this massless higher spin symmetry. And so there's some gigantic higher spin algebra that controls the whole thing. And so there's a much bigger symmetry algebra than you usually have in string theory. And perhaps this algebra is just powerful enough to fix the result and ensure that all the backgrounds are the same. I'm not entirely sure, but yeah, all right. I guess that was sort of open-ended, but I still thank you for your attention. Thanks.
Thank you very much.
Thank you.
Thanks.
Questions? Lorenz, could you tell me, could you explain more about why we should believe that the partition function factorizes in your explanation?
Yeah, sure. Let's go back here. So the idea would be that if you have this connected background, which is roughly this, then this would be the disconnected. So if you compute these partition functions, these give the same result. Mm-hmm. So on this side, it's sort of obvious that they factorize because you have really a string background that is a product, disconnected sum of two different things. So here it's clear that the partition function will be a product. So if you believe that this this thing that seems to hold at genus 1, that different backgrounds give the same boundary partition function. Mm-hmm. If you believe this also holds for disconnected background, then you get this equality. In particular, this guy, the existence of this guy doesn't spoil the factorization of the boundary partition function because it's just equal to this guy, and this guy factorizes.
So you have this example. I mean, this.
Yeah, yeah. Again, there's no computation that shows this. It's just extrapolating from the Thurman-Agius 3.
You working on this, or?
Yeah, I'm trying to work on it, but it turns out to be kind of difficult. So I'm not sure whether I will be able to do it. Yeah.
Can I ask a question?
Yeah.
So string perturbation, you argue that string perturbation theory is one loop exact in these theories. Yeah. There are other theories where the torus partition function in ADF3 CFT2 is one loop exact. And they all, like pure gravity or something like that. And they all follow from basically representation theory, like because you're computing a torus conformal block and the structure of the conformal block is fixed by perturbation, is fixed by group theory, basically by symmetry. Yeah. So do you think that there's a similar, so you might wonder, because you have the same result here, the origin is the same, namely that string field theory, if you were to do string field theory, at least in this case, there's some algebraic, you're computing the characters of some algebra, and they're therefore completely fixed as, you know, and I don't know, I mean, like, yeah. So for example, the one loop exactness of the pure gravity partition function follows from the fact that the characters of the Virasoro algebra don't depend on the central charge. So you might wonder if there's a similar explanation here, that you're computing characters of some algebra.
Yeah, I guess that sounds reasonable. I mean, there is this algebra, which is this super big extension of higher spin algebra, which is the one that appears at this tensionless point. Which is what's called higher spin square.
I see.
And that one is also super constraining the existence of this.
Right. Algebra. So, for example, could I reinterpret? And I see. So, would that be an alternate explanation for this, or would that be an explanation for this one loop exactness?
Yeah, at least it sounds very reasonable to me.
Okay. And so then your statement is that the higher genus partition functions are then conformal blocks for this algebra, right?
Yeah. From a boundary point of view, that's certainly true. Yeah.
Okay.
Yeah.
Thank you.
Yeah, but I think in 3D gravity is not clear. I mean, the perturbative, is it clear that also there cannot be, there are non-perturbative corrections, I guess?
Well, I mean, in pure gravity,
some of a different geometry.
When you try, well, to restore modular invariance, you need them in general, but your observation is that you don't in this particular.
Yeah,
in this particular theory, which is interesting. Good. Okay, thank you.
Yeah, thanks.
I had a bit of a vague question. So you mentioned at the end that this the fact that these partition functions are the same might come from some enhancement of this higher spin algebra. Do you have an understanding of how this might be related to these statements that are made in pure gravity, that maybe the disconnected and connected partition functions are equal because of some kind of a non-perturbative diffeomorphism invariance in purely in a pure gravity context? Like, do you think there's some sort of relationship between these? Like Jafferis and Maroff and Maxfield have some arguments that maybe you should expect that topology changing configurations are sort of, you know, gauge dependent, because there's non-zero transition amplitude from one to the other in pure gravity. So you shouldn't really think of them as two separate terms in the partition function. They're really the same thing. So I'm curious if this higher spin symmetry you mentioned is related to this.
Yeah, I don't know.
But Ben, that's a spatial topology. This is space-time, no?
Yeah, that is for you. Well,
spatial thing is obvious, kind of.
Well, no, it's not for spatial. Those are just Euclidean. I mean, it's just Euclidean wormholes.
Oh yeah, it's just slicing in a different way. That's why it's related by a transition amplitude. But this is space-time, I think.
Space-time. Aren't
it's
these both
different space-time topology, not the spatial topology?
There are some, I think there are some claims also by Jafferis, but they're not published, that this holds in string theory, even for larger flux, some similar story holds. But
yeah,
I think it's not so sharp, but I guess that's something different.
Yeah, it's just something, yeah, I guess this is stringy. My feeling is it should be string effect. I don't know, but it's not just simple slicing. Where do it thing.
Yeah, I mean, in particular, I think you need this winding for sure. So yeah.
Yeah.
I see. I had another question. So if you wanted to do this computation for the case of, the thing that you have on the side here for connected and disconnected.
Yeah.
So like in the Kotler-Jensen paper for pure gravity, the wormholes were supposed to be off shell, or in some sense off shell, but they're like close to being on shell. Is there like an analogous thing when you're doing these string partition functions, it's important that you're on shell, right? So is there some sort of slightly off shell thing you can do without going to full on string field theory?
Yeah, not that I'm aware of. I mean, you need to talk about some almost worldsheet theory or something like this. Yeah, I don't know. That's maybe something if you turn on some RG flow on the worldsheet and you go slightly away from the conformal fixed point, perhaps that's some analog. But yeah,
I see.
I wouldn't know how to compute anything with that.
Okay.
But yeah, perhaps that's a moral analog.
Okay. I just had one last question. Sorry,
Yes,
just
yeah.
a small question. That's just something I was confused by. So it was one of your earlier slides where you were talking about doing the sum over A, B, C, and D to compute the partition function before you got to the grand canonical ensemble. Yeah, I think right there somewhere. Yeah. So just a quick question. So in Witten-Maloney, you just end up summing over C and D, and you're supposed to think of the sums as like sort of large diffeomorphisms of the different ways of slicing the torus.
Right.
I just wanted to get a bit of intuition on why you end up summing over all 4 parameters here and how I should think about that.
Right. The Maloney-Witten CD is actually different. So because the CD corresponds to summing over the different geometries, right? So here this is one geometry. So it would be like the C to 1 and D to 0 term or something like this in there. So this sum corresponds to the ways. So here there are 2 tori. That's the main difference. There's a boundary torus, which you can think like this. And then there's the worldsheet torus. And the worldsheet torus can have like different orientations or wind several times. So if you think, okay, let me try to get, if you think about, so the maps from a 2 torus to a 2 torus, like just in homotopy. So there's the pi1 of the 2 torus is a Z2, and the pi1 of the target 2 torus is also Z2. Mm-hmm. So the maps in homotopy, homology, whatever, are like classified by 2x2 integer matrix. How this first pi1 is mapped to the second pi1. So you see that topologically there are 4 integers that describe this mapping. So these are these 4 integers. So if now you want to sum also over the geometry, which I don't, then you would have 2 additional integers actually.
I see.
Yeah, but one thing that also you should keep in mind perhaps is that in the end you have less than these 4 integers, because basically what you do, I mean, here you have 4 integers, but you have an integral over fundamental domain. The reason is that some of these integers are sort of correspond to just change of basis in this pi1, because you can do worldsheet modular transformations. So for instance, the S transformation interchanges 2 of these integers. And so what you can do is to sacrifice some of these integers to extend the region of integration. And that's basically why some integers go away. So these 4 integers mod the modular transformations.
Great, thanks. Yeah, that definitely clarifies it.
Can I ask you a question? So would you disagree with the following words, which is that because we're talking about a string theory where the ADS scale is string scale, there really is no, it's really not fair to call one of these bulk geometries a geometry, because there are no objects that are probing it on scales less than the ADS scale. So your observation could be interpreted as just saying that these strings just can't tell the difference between one of these SL2Z family of black holes and another.
Yeah, I would agree with this. Okay. So also, in fact, you can maybe even say even sharper that there is sort of no bulk in this theory, that the strings are always glued to the boundary. So for one thing, they're very large, so they cannot somehow resolve the details of the geometry, but also they're glued to the boundary. They always stick to the boundary somehow, so it doesn't matter what you put in the interior of that bulk. It doesn't change the actual string answer. So yeah, but I should mention that it's not super trivial. Actually, it's also more non-trivial perhaps than T-duality. So it is not, I mean, it's not true that the sphere partition function and the torus partition function are always the same. You have to add them up to get the same. So for instance, in the conical defect and the torus, there is different share. The sphere and the torus, they give different shares of the full answer. So I mean, I still think it's non-trivial that these two agree, but physically that's certainly the picture, I think. Yeah.
Okay, thank you.
But if you say those words, would you then be able, in the case of two boundaries, would you be able to tell the difference between the connected and the disconnected geometry?
Yeah, I think not. That's the point. Yeah.
I mean, I mean, your conjecture is that the symmetric product orbifold, you get the symmetric product orbifold answer. So your conjecture automatically says that everything factorizes between disconnected boundaries, right?
Yeah, right. But
right.
It's like somehow, but it should not be completely obvious that you get the symmetric orbifold answer. So there's still some kind of,
it should be the result of a calculation.
Yeah.
Right. Yeah. Right. So I mean, like you had this conjecture that like the partition function on disconnected is equal to the partition function on connected, but there I don't really know how. Presumably, your bulk theory doesn't even really know what it means for the bulk to be connected or disconnected, right?
Yeah, I mean, it does. In the definition, it knows because you start with some PSU WGW model or something like this. And
you're saying if depending on what subgroup you mod out by.
That subgroup, of course, knows.
No, but your string theory involves a sum over, you know, holomorphic, presumably some of our worldsheets propagating in this background, and it might not be sensitive to the full Fuchsian group or whatever, or to, presumably, like your conjecture is that it's not sensitive to which subgroup.
I mean, yeah, in the end, it's not.
It's not completely sensitive.
Magic cancellation, but in the definition it is. And also if you compute some one loop determinants or even higher loop determinants, then
yeah. No, I mean, if you work in perturbation theory, then clearly it is. But your conjecture is that the full string answer, the full answer, doesn't know about the group G. It only knows about the topology and conformal structure of SL2C mod G. So, okay.
Yeah, so in some sense, I'm also hoping that we could learn something about string perturbation theory, because clearly string perturbation theory is not the best method of doing this computation. But, I mean, as you say, you start with something that is highly redundant somehow and knows about many more things that you actually need to know. And also the whole moduli space of Riemann surfaces is basically not needed, because out of the integral, you just pick out certain, I guess, it becomes a sum.
And is it obvious that you're not going to need to include non-perturbative effects in the string perturbation theory once you're at genus bigger than 1? Because as you stated, it involves all genus stuff. And once you're doing all genus stuff,
right.
You have
although one thing is that if you're, so this is true in the grand canonical ensemble, but it's still, if you would extract a certain term in this sum, or if that is certain definition, then there is still a finite number of genera. So in the canonical ensemble, you have the genus expansion cuts. But yeah.
Good.
Yeah, and also it's for sure, in any case, it's not an asymptotic series. So it's a convergent series, contrary to usual string perturbation theory.
You mean this thing where you sum over all covers of your...
Yeah, I think that's a converging series. I'm pretty sure.
Is that right? Okay.
At least if you put the chemical potential high enough. I mean, you can always, because you have this P. I mean, there would be, I guess, complicated phase transitions. But if you take this P to be e to the by sigma, and the sigma you take large imaginary part, then you sort of suppress complicated covers.
But you're saying that the number of n-fold coverings of a genus G surface grows only power law. It grows at most exponentially in n, I guess is what you're saying.
Yeah, I think there are roughly n to the G.
Yeah, okay. So there's no factorials.
So there are for sure 2 to the G covers of degree 2. I think in general there it's n to the G.
I see.
correct.
That sounds okay, perfectly reasonable. Great. Thanks.
Thanks.
Any more questions? If not, let us thank Lorenz again.
Thanks.